We'll consider our next paper from Nidhi Bhatt, the comparative analysis of hybrid cryptosystems for secure image encryption. Ma'am Nidhi.
Yes, sir. Good afternoon. I will be presenting online. Good afternoon, everyone. This is Nidhi, doing BTech CSE from Indira Gandhi Delhi Technical University for Women, and I will be presenting my paper, Comparative Analysis of Hybrid Cryptosystems for Secure Image Encryption. Introduction. Safeguarding sensitive images is vital, especially within the PKI systems. Satellite images are more complex and cover larger areas, requiring more advanced processing compared to normal images. Satellite image encryption is crucial to protect the sensitive data from manipulation. Traditional methods such as DES and triple DES are not suited for images due to their large size. So this study compares two hybrid crypto system for satellite image encryption, AES-GCM and Chacha-Poly, and both systems use ECDH for key exchange and respective algorithms for bulk encryptions similar to TLS 1.3. So they are evaluated using metrics MAC, PSNR, SSIM, entropy, total encryption, decryption process time, NPCR, USCI, correlation coefficients, and bit error rate, BR. So this slide presents the literature review in the context of image encryption. So as we can see, so there has been very little work presented in satellite image encryption. And moreover, the direct comparison of AES-GCM with Chacha-Poly with ECDH key exchange in the context of image encryption has not been presented before. Research methodology. So this experiment is done using Python in a cloud-based Kaggle CPU environment, which provides a 4-core Intel Xeon processor with 30 GB of RAM. So the key step involved are as follows. ECDH key pair generation using P256, shared secret computation via ECDH algorithm, key derivation using HKDF, image database. So 10 satellite images from deep globe land cover dataset was used for testing. And for each image, the following steps are performed: encryption and decryption, matrix calculation, and visualize encryption strength and store results. And then finally, read and display results for all images and generated time comparison plot as shown in the figure. So this is how the experiment was done, the implementation. So for key exchange, key pairs were generated using ECDH, and then exchange the public keys, compute shared secret, use HKDF to derive the final symmetric key. For AES-GCM, SHA 384 was used, and for Chacha-Poly, SHA 256 was used. For the encryption process, read and flatten the image data, generate 12-byte nonce using os.urandom. So this is a Python function. I have not used this sequence number here to generate the nonce. Initialize with 32-byte shared key, encrypt data with associated data for integrity, then reshape the encrypted data to original image dimensions, then record the decryption time. Similar process for decryption, receive encrypted data, nonce and image shape, initialize with the same shared key, verify authentication type if valid, decrypt data, if not, then the verification phase, then halt. So this is how the proposed implementation compares with TLS 1.3. Similarities: ECDH key exchange is there, cipher suits, implements AES-GCM and Chacha-Poly. Key derivation uses HKDF, nonce generation, 12-byte nonsense. Authenticated encryption employs AEAD. Hash functions uses SHA 384 and SHA 256. Dissimilarities are there, so there is no certificate verification. Uses fixed key pairs instead of generating new ephemeral keys for each image. So there is this specific use case. So it's used for image encryption, rather than general purpose communication, simplified nonsense handling is there. So this does not include a full network stack integration or practical demonstration of HTTPS SSL. So the focus is on the cryptographic operations. Now to the results and discussion. So both the systems show similar security performance. And the comparison is based on the average of all the metrics calculated across the set of images used for testing. So AES GCM is faster in all time metrics, as we can see here. Near idle NPCR and UACI values, and both achieve maximum entropy. Average correlation values for the encrypted images is near 0, which is good. So it's continued. So as we can see in the figure 1, for the encrypted image, so there are no visible patterns, and the decrypted image is identical to the original with bit error is 0. So this shows the lossless nature of the process. Onto the next figure. So we can see that AES GCM is faster than Chachapoly. So some potential reasons for that can be the hardware acceleration for AES and the specific implementation environment. And decryption is faster than encryption due to additional operations in encryption, as we can see here. So there is noise generation here. Then continued in correlation analysis. So we can see for the original image, strong patterns are there. And for the encrypted image, so there is this uniform distribution. For the histogram analysis, so we can see for the original image, distant peaks are there, and for the encrypted histogram, near uniform distribution is there across all pixel values. So future work and conclusion. So some future work can be the integration of PKI algorithms, for example, Kyber and dilithium. Testing with diverse image types beyond satellite imagery. Optimization for resource constrained environments in PKI environments, for example, in handheld devices. Advanced security analysis using NIST test and grade level co-occurrence matrix analysis. Comparative studies with OpenSSL and Wolf SSL TLS 1.3 suits, and full SSL HTTPS protocol stack integration and performance testing against TLS 1.3 latency requirements. So finally, this research can be concluded as follows. Now, the both system exhibit robust security features, and AES GCM outperforms Chachapoly in speed, approximately 13.33% faster overall. And some practical application of this work can be enhancing the digital image security in PKI systems and potential use in e-governance and IoT applications. These are the references. And thank you. And I thank Mr. Prabhat Kumar, scientist DMET, for his valuable guidance and insights for this paper. Thank you.